Sometimes even two Gaussians are not sufficient to model the heavy tails of the distribution of log returns. We can then use a mixture of k Gaussians. The PDF of a mixture of k Gaussians is given by the sum from k equal 1 to capital K of pk times the normal PDF of parameters mu k sigma k. The variable z takes values between -infinity and infinity. P is a probability vector whose components P1, P2, up to P capital K are non-negative and add up to 1. Pk is the probability of the kth component in the mixture, which is a normal distribution of parameters mu k sigma k. Let's define the vector of means, mu, which is equal to mu1, mu2, up to mu capital K, and the vector of standard deviation, sigma, whose components are equal to sigma 1, sigma 2, up to sigma capital K. Including more Gaussians provides more flexibility in the modeling process. However, the number of parameters also becomes large and there is danger of overfitting. We say that a model overfits when it describes well the observations used in the fit, but fails to provide a good description of other samples from the same distribution which have not been used in the fit. The best rule is to use Occam's razor. Choose the smallest number of Gaussians so that the mixture fits the data reasonably well. For instance, a mixture of 3 components usually provides a good model for financial log returns. To generate a sample from a Gaussian mixture of parameters p, mu, and sigma, we first generate a sample from a categorical distribution of parameters p and capital K. The second step is to generate a sample from the normal 0,1 distribution. Finally, we compute z equal to mu k plus sigma k times x, which is a sample from the Gaussian mixture. Let's now write a program that implements this algorithm. In this demo, we're going to generate a matrix with 1,000 rows and 100 columns of random numbers that follow a Gaussian mixture distribution with 3 components. The parameters of the components are specified here. The first parameter is the probability vector that gives us the probabilities of each of the components in the mixture. Here we have a mixture of 3 Gaussians. The first one has probability 1/2, the second one has probability 1/3, and the third one has probability 1/6. The sum of these 3 probabilities is equal to 1. The first component in the mixture has an average of -1 and a standard deviation of 1. Second component has mean 4, standard deviation 3. The third component has mean 12, standard deviation 0.5. To sample from the Gaussian mixture, the first thing we're going to do is to simulate a matrix of m rows and n columns of categorical random numbers whose probability vector, p, corresponds to the probability of each of the components in the Gaussian mixture. So xi, in this case, will have values 1 corresponding to component 1, 2, component 2, and 3, component 3. To generate random numbers from the Gaussian mixture, we're going to generate random numbers from each of these components and then select with the vector of indices, which is defined here, the component that we are generating. So, for instance, when xi is equal to 1, we're going to generate random numbers from the first component of the Gaussian mixture, so the one that has mu1 and sigma 1. For the second component, we'll do the same thing for mu2 and sigma 2, etc. And finally, here is how the scale histogram looks when compared to the PDF. We see that we have generated random numbers whose distribution is a mixture of 3 Gaussians. First Gaussian, second Gaussian, third Gaussian.